So we have explained the physical meaning of the transition to a curvilinear coordinates in flat space-time. The physical meaning is just transition to another not necessary inertial reference frame if in the coordinate transformation we mix spatial and time coordinates. Now, what is the physical meaning behind curved spacetimes will be explained in the upcoming lectures. But at this point, let me make some exercise here, which will be relevant for the discussion of curved spacetimes. But let me stress that even if we consider curvilinear coordinates, metric in spacetime can look unrecognizable. So it means that it can be some function of x, dx alpha, dx beta, and this can be some. It won't be obvious from the form of this metric whether we are dealing with flat or curved spacetime. How to distinguish flat and curved spacetimes we will describe in the next lecture. But once we are considering a generic metric tensor, let us describe a motion of particle in such a generic metric. The motion of particle we can describe using minimal action principle. To use minimal action principle, we have to write an action for a particle in curved spacetime. If we have a particle in curved spacetime, suppose we have in arbitrary curved spacetime. It can be flat spacetime in curvilinear coordinates. It can be flat spacetime in flat coordinates. It can be curved spacetime. If we have a particle and its world line, the unique invariant characteristic one can write for this world line, its length. So it is natural to expect that the action will be proportional to the length of the world line of the particle. The reason why we are looking for the invariant action, invariant means with respect to the coordinate transformation. The reason why we are looking for the invariant action, because we expect that from the minimal action principle for this action, we expect to get equations which are covariant under the coordinate transformations. Covariant means that they look the same in different coordinate systems. The equations of motion. The reason why we are looking for the equations of motion which are covariant under the coordinate transformation is this principle of general covariance, which I have just explained to you. We want to have equations of motion which are looking the same in different coordinate systems. So the invariant characteristic is the length, and also in flat spacetime it was obvious that the extremal action will correspond to the straight line. So it's natural that the action is just a length. So let us write the formula for the length. To write the formula for the length, we have to approximate the world line of the particle by a chain of straight intervals. And when the intervals are short, we can approximate the length of each element, each segment. For example, the eth segment. Length of the eth segment is just g mu nu of zi plus 1 minus zi mu times zi plus 1 nu minus zi nu square root. So this is just ds. And ds squared under the square root along the world line of the particle, along this segment of the world line of the particle. As a result, the length of the world line is just the sum of this, guys. Sum over I from 1 to n. Now, if we want to obtain the smooth world line, we have to take n to infinity, number of segments to infinity, and the size of each segment to 0. As a result, we obtain that the length is just the integral of ds over the world line of the particle. And at the same time, this is just tau 1 to tau 2 d tau square root of g mu nu of z of tau z mu dot, z nu dot, where dot means the differentiation with respect to tau. Tau is just a parameterization of this world line. Notice that we can choose any parameterization of this world line. We can change from tau to f of tau as long as f dot of tau is greater than 0. Because then, if we just use this coordinate change, we will obtain that this is equal to df f1 f2 square root of g mu nu dz mu df dz nu df. If this is valid, f dot of tau is greater than 0, then we can extract this from the square root and cancel and change to a different parameterization. Tau and f are just different parameterization of the same world lines. And this thing just says that we have to respect the order of points along the world line. So the action then is just minus m integral of tau 1 to tau 2 square root of g mu nu of z, which is a function of tau in its own right, z mu dot, z nu dot, d tau. So this is the action. The reason why we have m here, the reason why we have minus here is very simple, because actually the longest line is the straight one in Minkowskian signature, the longest one. Among the all lines, those which are having, no, but first of all, let me, okay, minus m here is just due to complementarity. If, for example, this metric is just flat Minkowskian metric, we obtain just the standard action for the particle, relativistic particle in Minkowski spacetime. I just remind you why there is a minus sign here. In Minkowskian metric, minus sign here is necessary because actually among all lines whose tangential have angle less than 45 with respect to the vertical line, among all these lines, the straight one has the longest length. So this, unlike the Euclidean geometry, in Minkowskian geometry, the straight lines have longest lengths among those which have angle less than 45 degrees with respect to the vertical line. So, and that explains why we have minus sign, because we want to have, for the longest line, we have least action. We want to have least action.